Hello, students. In continuation to our previous topics, that is Bohr's atomic theory and Sommerfeld's extension of Bohr's theory, let's talk about wave particle duality of electron today. In 1905, the Albert Einstein he proposed that the light has a dual character. Dual character means it has not only the wave character but it also has the particle character. And in continuation to his work, the French physicist Louis de Broglie he proposed that the matter also has a dual character just like that of the light, and he won Nobel Prize in 1929 in physics for his work. So as we all know that in Bohr's theory, the electron it is treated as a particle. Okay, but the de Broglie theory suggested that the matter it is including all the subatomic particles, that electron, protons, etc. So like matter, the electron also has a dual character, that is having both the wave character as well as the particle character. And he derived an expression where he tried to relate the wavelength of the particle which is having a mass m and moving with the velocity v, and this is the de Broglie equation, that is the lambda is equal to h upon mv, where lambda is the wavelength, h is the Planck's constant. I hope you people are aware of Planck's constant. M is the mass of the particle and v is the velocity with which the particle is moving. So the de Broglie equation, it is lambda is equal to h upon mv. H is Planck's constant, m is the mass of the particle, and v is the velocity with which particle is moving. Okay, now this de Broglie equation it can be easily derived from the einstein's Einstein's mass energy relationship. And what is the Einstein's mass energy relationship? Einstein's mass energy relationship is E is equal to mc square. This is Einstein's mass energy relationship and where E is the energy, m is the mass, c is the velocity of light. So energy it is related with mass and square of the velocity of light. And if you remember, then there is another relationship of energy where energy of any wave it is equal to h h nu. Energy is equal to h nu, where again h is the Planck's constant, nu is the frequency of light. Nu is the frequency of the wave associated. So E is equal to h nu, and if we equate these two terms, because these are the energies which are relating the different things, so h nu is equal to mc square. We can say that h nu it is equal to mc square. And from the relationship of frequency and wavelength, we know that nu is equal to c upon lambda, where c again is the velocity of light, lambda is the wavelength of light. So we can, in place of nu, we can write c upon lambda. So your left hand side of this equation, equation it becomes h c upon lambda is equal to mc square. Now here you can see that in both sides, that is in left hand side as well as in the right hand side, we have the velocity of light. So this velocity of light cancels one velocity of light in the right hand side, and then your equation becomes h upon lambda is equal to mc. Okay, now we are interested in finding the value of lambda. So what we can do, we can take lambda to this side, that is towards the right hand side, and mc, it comes here in the denominator, and your equation becomes h upon mc is equal to lambda, or lambda is equal to h upon mc. Okay, so again here c is the velocity of light. Now suppose we want to use this equation for any particle which is moving with the which is having a mass m, and it is moving with the velocity v. So we can replace the c with velocity v. So we can say that your lambda is equal to h upon mv. We have done nothing, we have just replaced the velocity of light c with a velocity, any velocity, that is v. Means here now the mass, it is not moving with the velocity of light, but rather it is moving with velocity of v. Okay, v is the velocity. Now there is another relationship we know, where the linear momentum, if you people remember, it is the product of mass into velocity. So here the linear momentum p, it is equal to mv. So we can replace the term mv here in this equation with the p, which is the linear momentum. So we can say, we can write it as lambda is equal to h upon p. Okay, where p is the linear momentum of the particle. So these are the different expressions of de Broglie's equation. De Broglie's equation is lambda is equal to h upon mv. This we have derived from the Einstein's mass energy relationship, that is energy, it is equal to mc square. Another form of energy, that is of the light, it is equal to h nu, where nu is the velocity, the frequency of the associated wave. Now we have equated these two things. C is common both sides, so this one c, it cancels the one c in the right hand side, and we get the formula lambda is equal to h upon mc. Here we were saying that the wavelength, it is associated with the mass and velocity of light. If we replace this velocity of light with any velocity, then your then your formula becomes lambda is equal to h upon mb. And from the knowledge of the definition of linear momentum, that is p is equal to mv, we can write this expression as lambda is equal to h upon p. Now can we use, this relationship, this de Broglie's equation, we can use for calculating the calculating the wavelength of any particle which is moving with different velocity, if we know the mass of that particular particle. So let's do an example or a numerical here. So in this problem we are given that calculate the de Broglie wavelength, of electron. Now just read this sentence carefully. Electron moving with a velocity of 1.20 10 raised to power 5 meter per second. Now just read this the statement carefully. We are asked to calculate the de Broglie wavelength of the electron. Just this is the electron. Okay, for the electron we are going to calculate the de Broglie wavelength, which is moving with the velocity of 1.20 into 10 raised to power 5 meter per second. Now again I'm writing the de Broglie equation, that is lambda is equal to h upon mv. Now h is the Planck's constant. It is a constant and its value is 6.626 into 10 raised to power minus 34 joule second. Please remember, nobody is going to give you these values. You are final year student, so you must be knowing all these values. Okay, and m here, if you see, we have to calculate the wavelength of electron, so you must be knowing the mass of the electron, and mass of the electron is 9.1 into 10 raised to power minus 31 kg. Okay, and velocity, it is given 1.20 into 10 raised to power 5 meter per second. Okay, now put this value here, or your lambda becomes h upon mv. Write the value of h, 6.626 into 10 raised to power minus 34 upon 9.1 into 10 raised to power minus 31 into 2 1.20 into 10 raised to power 5. And when you will solve all these things, you will get the value comes out to be 6.068 into 10 raised to power minus 9 meter. This is your lambda value for the electron, which is moving with a speed of 1.20 into 10 raised to power 5 meter per second. Okay, so I am going to give you another numerical problem, which you are going to solve. Okay, and this is the calculate the de Broglie wavelength of a body of mass 1 kg moving with a velocity of 2000 meter per second. Okay, so next time when we will meet, I am going to ask you the answer. In fact, one thing you people can do, just write your just find out the value of this, and you can also text your answer in the WhatsApp group. Okay, so this numerical you are going to do. Okay, so okay, let's I'll again send you another topic video lecture of the next topic. Then we can discuss this numerical also. Okay, so bye, take care.